Cool. All right, now how do I? Yeah. All right. No. Present. Okay. I think Arun, didn't you kind of do an overview of this at the whatever the open track sessions or whatever?
I did, but it was very fast, and also not everyone was there.
Yeah.
So we should definitely go through it.
I mean,
For
yeah.
everyone, we have a bad habit of kind of falling into jargon and just using terms that we're familiar with, but might
Oh
not be
yeah.
familiar to everyone because you haven't been working with this stuff for years. So
Yeah.
please stop us and ask questions if nothing makes sense.
Yeah. That's yeah, there is a lot of like technical jargon and stuff that you'll pick up throughout this, but at the beginning, as Arun said, like please feel free to interrupt me or message in the chat. Hopefully that comes up when I'm presenting. I'm
I'll keep an eye on
also
it.
hold on, going to turn off my video because my Wi-Fi sucks and it
I'm
might
also going to drop the link to
kick
the.
me off if I. There we go.
I'll drop the link to the presentation in the chat in a second if anyone wants to follow along or
Yep.
look back on stuff.
All right. So, as I said, this is intro to propulsion, and so today's lecture is just going to kind of be an overview of, propulsion and stuff in general, and then we're going to talk a little bit about the engines that we've made in the club so far. How do I? No. Okay. So first of all, what is a propulsion system for anyone who doesn't know? So a propulsion system is basically anything, any system, mechanical system that produces thrust. Generally, at least in the context of aerospace, uses Newton's third law of motion. So the concept of for every action, there is a reaction, and accelerates some kind of working fluid. Whether it's most of the time, it's going to be some kind of combustion exhaust gases. So it accelerates this fluid and creates a reaction force on whatever vehicle you have, whether it's a rocket, airplane, whatever. So as I said, the majority of propulsion systems will use some type of combustion. So a pretty basic overview is combustion, you need a fuel and an oxidizer. I think everyone in the poll said they've taken AP Chem, so I hope this is a bit of review. And if you haven't, fuel is any type of chemical compound that will react with oxygen to release heat energy. So this is hydrocarbons like gasoline, alcohol, methane, and then oxidizer is mostly oxygen, but any oxygen containing compound that will oxidize one of those fuels. So most commonly oxygen, nitrous oxide also works as a oxidizer, and hydrogen peroxide is also an oxidizer. So there are a few different types of propulsion systems in aerospace. So you have high-powered rocket engines, which we'll talk more in depth, and pretty much what this course is going to focus on. So those are liquid-powered, hybrid-powered, and solid-powered, and we'll cover those more in depth in a few slides. And then you have low-powered rocket engines. So those are like cold gas thrusters, ion engines. Is that a cool picture of an ion engine? I think that is.
Yeah,
Yeah.
that's one piece.
And then cold gas thrusters, pretty much, there's no combustion. They just use compressed gas, and there's your action reaction as it releases the cold gas. You have gas turbines, like here on the right. By the way, I ask this like every meeting, but can people see my mouse?
Yes.
Yes.
All right, cool. So you have gas turbines, like this picture over on the right here. So there's a few different types of those, turbojet, turbofan, turboprop. We won't really get into that much, but basically a turbojet is what you see here. And then a turbofan is when you have a turbojet powering a giant fan. That's turbofans are what's on most commercial aircraft. And then you have turboprop, which is pretty much a turbojet powering a propeller. And then you have air-breathing rocket engines like ramjet and scramjet, which I think this is one right down here. I really don't know about ramjets and scramjets, but you know they are a type of propulsion system.
Does anyone know about ramjets and scramjets?
I'm not sure if anyone here in the club does, but that would be an interesting topic to expand upon once we're done with Regen. All right, so solid rocket motors, pretty much what most hobby rockets use. So basically you have a solid fuel and a solid oxidizer formed into a solid fuel grain. This is, you know, pretty much just like the common Estes motors. So these generally have low efficiency, but they also have a very low inert mass. Almost none at all if you are considering like these Estes motors. It's just a little cardboard casing around it, and the rest of it is pretty much fuel and oxidizer. So these are best used for very small rockets since they don't have much other mass associated with them. And then the burn characteristics are kind of fixed by the grain geometry. I'm not really going to get into that. There's a lot there that if anyone is interested in solid motors and wants to start that, by all means, there are some schools like MIT that do their own custom solid motors, but that's pretty dangerous and not something this club has ever looked into doing. But the majority of our rockets in the club are actually launched on commercially bought solid motors. So just to, you know, be aware of solid motors, they're a thing. So liquid motors, which is pretty much what this course is going to focus on. Basically, liquid engines combust a liquid fuel and a liquid oxidizer. Sometimes in the case of one of our old engines, it's actually a gaseous oxidizer. But so they just combust fluid, liquid or gas propellants in a combustion chamber and spew it out a nozzle to make thrust. So these are the fuel combinations are more efficient at large scales. There's a lot more inert mass than solid motors. So you have like the engine itself, and then you have the tanks to store all of the propellants and stuff, and the whole feed system of tubing. And on larger like orbital scale rockets, you'll have turbo pumps to drive the fuels. But if you scale that up, liquid engines have a much higher thrust to propellant mass used. So that's generally why they're used on larger scale rockets. You also have a lot more control over the thrust and burn duration that you get out of the rocket engine. Some rocket engines are even throttleable, not the ones that we build. One big thing is that liquid engines are much more complex to design, and generally only college groups and only a few college groups are the only amateurs to attempt building liquid rocket engines. So yeah, pretty complex stuff that we're going to be talking about this semester, but don't worry, we're making it completely digestible to freshmen and people completely new to rocketry and engineering in general. So yeah, a lot of fun stuff. And of course, liquid is what we're working on for the dollar per foot challenge with the Regen engine. Actually, before I go on, is there any questions? All right. So the last type of high-powered rocket engine is a hybrid engine. Basically, you have a solid fuel grain and a liquid or gaseous oxidizer. I don't think I've ever seen one that has a solid oxidizer and a liquid or gaseous fuel, but who knows, could be possible. Usually for a hybrid, the solid fuel grain is something like I think some kind of plastic will work for this since that's a hydrocarbon. And yeah, basically you flow your oxidizer over it and that will combust on the inside of the fuel grain and come out the nozzle, just like in a solid or liquid. So in theory, hybrids exist because it has the benefit of being efficient like a liquid rocket engine, but less complex than a full liquid engine because you only have to deal with one propellant tank, and the fuel grain can actually work as the combustion chamber. But in practice, you kind of just get the worst of both worlds. It ends up being less efficient than a liquid, but heavier than the equivalent solid. So hybrids aren't generally used in commercial rocketry, but there are quite a few hobbyists who kind of use it as a step between solids and liquids. All right, I'm going to defer to Arun on this slide because he is the resident expert on gas turbines and ramjets and scramjets because he did his capstone project on gas turbines.
Yeah, we're not going to spend too much time on this because the focus of this is on liquid engines, but basically you don't need to carry your oxidizer because you have the air that you ingest. With gas turbines, it's a normal jet engine. You got a big ass compressor on the front that pulls in air, combustion, and a turbine behind it that powers the compressor, and then a nozzle. Ramjets and scramjets are cooler because they're just they skip that compressor and turbine stages. They only work at supersonic or near supersonic speeds because they actually use the speed to compress the air using fancy shockwave stuff that we're definitely not going to get into. But they have a lot of benefits in atmosphere flights because, again, you only had to carry the fuel, but also they have the power of a rocket engine. None of these work at very high altitudes like space because there's no air, and they generally really suck to design gas turbines because compressor and turbine design is a terrible time, and ramjets and scramjets because supersonic compressors that use shock waves are even worse to design.
Yep. Also, again, I've kind of caught myself using some of the technical jargon. So propellants basically refer to both fuel and oxidizer. Both of those are one of your propellants. I think that's all the stuff I've used. Again, if I use a word and you guys don't know what it means, like please interrupt me or put it in the chat. Okay, so as I said before, this course is mostly going to focus on liquid engines. So we're going to go over a few of the major components of liquid engines and kind of an basic overview of how they work. So there are three main parts to a liquid rocket engine. You have the feed system and injector, the combustion chamber, and the rocket nozzle. Also, Arun, I don't know what time it is. It's not showing on my computer because I'm in full screen mode. So if you just want to cut me off at 9, I don't want to go over.
You're good. It's 8:30.
Oh, cool. We have plenty of time. Yeah, so those are the 3 main parts. If you see in this diagram here, all of these tanks labeled helium, LOX. LOX is liquid oxygen. You'll commonly see that referred to in a lot of the stuff, especially with ZPF, because we're using liquid oxygen as our oxidizer. And then the helium tank. Yeah, another thing is if there's an L in front of something, that generally means it's cryogenic liquid. Add something.
Did you say helium tank?
Yeah, or
What is
yeah,
that for?
helium. Yeah, okay. So there are a few different ways you can design a feed system. The one that we're doing and is better for small applications is what's known as a pressure fed system. So basically you need to push all of your propellants into the nozzle and the rocket engine. So your chamber is at a certain pressure and you need a higher pressure inert gas. So helium is inert. It doesn't react with anything. So you can use that to push out your oxidizer and fuel and pretty much just force it into the combustion chamber. So that's what this whole section is the feed system injector section.
That's the liquid oxygen thing that Jackson was talking about, and then the LH in this diagram is liquid hydrogen, which is a fuel. That's what the space shuttle main engine uses for fuel. People at our scale super don't do that because we don't have a death wish. It's really efficient, but also that's how the Hindenburg happened, except not even liquid. So yeah, we don't work with that. We'll usually use something like liquid methane or kerosene or an alcohol.
Yeah, a lot of propellants are actually pretty scary, so we avoid a lot of them. Yeah. But anyway, yeah, so the feed system injector stores all of your propellants. It delivers them when the engine's firing. And then you have the injector. Its purpose is to mix and atomize the fuel and oxidizer. So basically, atomization is when you pretty much aerosolize it, I guess, make it as much of a fine mist so that it's well mixed and combusts really evenly. And you get complete combustion of your fuel. So then the combustion chamber is kind of this section here. So the combustion of your fuel and oxidizer is going to be it's basically a pretty high pressure controlled explosion. So the combustion chamber needs to be designed really well to contain all of that pressure and make sure it doesn't overheat and melt during firing. And then the nozzle is the last part and the most fun part. It takes your combustion gases and squeezes it through a converging diverging nozzle, which is something that we're going to be taking a closer look at. And basically it accelerates it to a useful speed, because remember we were talking about the propulsion system works on the basis of action reaction. So you have an action of throwing a bunch of really hot combustion gases at very high speeds out the end here, and that creates a thrust force. And basically the faster that it's going, the more thrust you're going to get. So yeah, the nozzle works to really accelerate everything, and a good rocket nozzle will accelerate the exhaust gases to supersonic speeds, which supersonic flow is very fun. Lots of fun math there. All right, are there any more questions on this slide?
I had a question about the DPF rocket. Will it be dealing with supersonic flow out the nozzle?
Kind of fading out there.
Yeah.
Will it be dealing with a supersonic flow out the nozzle?
Yes.
Yes, very much so.
Yeah, we don't have supersonic flow out of the rocket engine. It is a flamethrower and will not make a lot of thrust. We'll get into that more later, but that's choked flow is how you achieve supersonic exhaust, and that's really what we want.
Oops. Yeah.
Did you say what the purple thing was? And I missed it.
This purple thing?
Yeah.
Yeah, that's pretty much just a valve, I think.
Reg.
Oh yeah, regulator. Basically the regulator here would set your pressure on this side of the tank. So you have super high pressure helium, and then I won't get too much into the fluids of it, but you need a constant pressure in these tanks to deliver the right amount of flow rate. So this just regulator makes sure that the as this tank drains and depressurizes, it keeps the same constant pressure on this side of it.
Okay, thanks.
The regulator will make sure like it's not equal, right? Like it probably won't have equal pressure for the top of the liquid oxygen tank as the top of the liquid hydrogen tank, I assume.
Yeah, so well, it's a little bit complicated. In some systems, in our system on the DPF rocket, we actually have two regulators. Um, it pretty much just determines the pressure between the high pressure helium and whatever is on your low pressure side. Um, yeah, for us, we have two regulators because you're right, the pressures in each of these tanks are different. But there are some, I think, like the Methylx engine, which we'll talk about in a minute. Uh, they somehow tried to use the same pressure in each tank. So, but that's a headache. All right, if there are no more questions. Oh, cool. I already covered the first two bullet points. And that other bullet point. Yeah, so pretty much, as I said, the nozzle, or the entire rocket engine pretty much is, the basic function is you take a fuel and an oxidizer and efficiently combust it and efficiently accelerate it to supersonic speeds to generate thrust. And the basic principle of how thrust is generated is conservation of momentum. So if everyone remembers from physics, mass times velocity. So here we have the engine is basically throwing a bunch of gas particles, which have mass, out of the nozzle at very high speeds. So that creates a momentum and a thrust force. And then, so the parameters of a rocket engine that you kind of can play around with are the fuel and oxidizer selection, chamber pressure, flow rates of your propellants, and the contour and design of the nozzle. Okay, yeah. So are there any more questions about either of these slides before we get into what the club has already worked on in the past? All right. Aaron, how are we doing on time?
You're good.
Cool. So in the past, the club has worked on 3 different engines. The first one of which was the IPAGOX engine, isopropyl alcohol and gaseous oxygen. The next one that the club did was the Methylx engine, liquid methane and liquid oxygen. And then the last one, which is being used for the DPF rocket, is Regen, named after not its propellants, but its cooling method. This one is regeneratively cooled, which means it's pretty much cooled with its fuel, which is something we'll talk about a lot later in like a month or so. all the different cooling methods, but yeah. So the IPAGOX engine, as I said, isopropyl alcohol, gaseous oxygen, 50 pound-force of thrust. Here's a picture of it. Very, very big and chunky. Pretty much just a proof of concept ground test engine that some kids made to start off LRE and kind of, explore what they could do. I don't think this engine was ever actually fired successfully. I think I remember there was an issue with ignition, something that no one had thought about. They couldn't figure out how to ignite the engine once they had it made. And by the time they were there, they were already a good amount of the way through the Methylx engine. So nobody bothered to actually hot fire this guy, which is sad. But one of the things that we hope to do with you guys actually is so we're going to have you design all your engines to be around this scale, just to keep it simple, not do anything too crazy, and hopefully we'll be able to use the feed system that they in the test stand they built for this engine to hot fire one of your guys' engines in the spring, which depends on COVID, but hopefully we'll figure out a plan to work around that and get you guys working on that, upgrading that feed system and hot fire one of these engines in the spring. So the next engine, the Methylx engine, is one that we actually hot fired. So it's, again, liquid methane powered and liquid oxygen powered, 350 pound-force of thrust. So this one was actually built as a capstone project by a few of the club members. And it was built to fly on a rocket in the Far Mars competition, which was basically, oh, by the way, Far is Friends of Amateur Rocketry. They are the ones hosting the dollar per foot competition we're doing with the DPF project, Redshift, whatever it was advertised to you guys as. So it was built for the Far Mars. The Methylx engine was built for the Far Mars competition, which I think that rocket was a collaboration between us and a bunch of other schools. I want to say RIT, Georgia Tech, and Virginia Tech.
For reference, it was because a bunch of people who were interns at SpaceX together were like, let's build a rocket for fun.
Yeah.
And then the engine got built because that was our part. The rocket didn't get built because that was other people's part. So
yeah, that don't do projects cross school because that sucks. But yeah, so this engine was hot fired in the summer of 2018 and is currently the only engine that the club has hot fired. We are hoping to change that this semester by hot firing Regen. But yeah, it never, obviously, I say it was built to fly on the rocket at the Far Mars. It didn't actually, because as Arun said, the other teams didn't exactly deliver on their side, sadly.
which might not have been a bad thing because every team that actually did try to launch a rocket with this blew up.
Yes, this is also true.
Yeah, I think the highest one that anyone got was about 56 feet off the pad. So
Yeah,
at least we didn't blow up.
this is true. All right, actually, should I mention this? This was a successful hot fire, semi-successful hot fire. Nothing exploded, so that's good.
Does static fired or like hot fire just mean that it didn't go up in a rocket?
Yeah, basically. Yeah, static fire is just when we go up to Maine or wherever our test site is, ends up being, and we strap it to a big heavy test stand, and it doesn't leave the ground. All right, so Regen, this is the engine that me and Arun have both been the closest involved with in developing. So this one is kerosene and liquid oxygen powered, 750 pound force of thrust. It's designed for the DPF competition rocket, the Redshift rocket. We are currently working on manufacturing it. We're going to be metal 3D printing it out of Inconel, which is a very, what is it? It's an alloy. What is it? It's an iron nickel alloy.
Yeah.
Yeah, that's
really expensive. That's really what we care about. Really expensive and really good.
yeah, really expensive and worse. Has really high strength at high temperatures. So yeah, we're currently working on manufacturing this. We actually have a metal 3D printer in our capstone lab that we're have been struggling with all summer with the administration on getting it up, but it's finally up and running, and yeah, we're planning on manufacturing it this fall and hot firing it on the same test stand that the Methylx was fired on by the end of the semester or early next spring. And as I mentioned, the name comes from regenerative cooling, using the kerosene as a coolant. So that's why you have these two ports on the side here. The kerosene flows down, flows into this port, flows down to the bottom of the nozzle, and then back up through the whole chamber and comes out here to go back into the injector. So that cools the combustion chamber and the nozzle without having to carry extra coolant, because we're using the fuel as our coolant, and it also, all of the heat energy lost to cooling ends up going back into the fuel, so helps with overall efficiency.
In contrast, the IPAGOX engine, the first little one, just wasn't cooled at all. It just has a large amount of stainless steel in the wall. So it's only made to be fired for about 7 seconds because it's very much a test engine. And the Methylx engine, it's literally made with a disposable inner wall coating. So it's also limited in its test fire length. Yeah, this is the first one that we can, if we have unlimited fuel, in theory, could just fire forever. Now, how all that's actually applicable is for what the rest of this semester is going to look like for us. You actually want to kick it over one slide? Now we're tight on time.
Oh, we are.
Yeah, so basically we're going to be doing this meeting slide. It'll be more of these kind of presentations, but a lot more in depth into each kind of design phase and what theory goes with it. We don't want this to just be another class because online classes suck. So it's going to be a lot more of design integrated into the why does we design things the way we do. And then the Thursday sessions will be working sessions and question and answer times for everyone, because we will be working in small groups, just because doing this alone is kind of difficult. And also we don't have the bandwidth to keep track of 25 engines. I think there's a slide after this, right?
Just a question slide.
What happened to the summary slide?
The summary slide? I don't know what happened to the summary slide. I never made one. Did you?
It skipped a slide between Regen and this. There it is.
Oh, whoops. I don't know how that happened.
I was wondering. Okay.
Okay.
So basically this is what we're looking at overall. As I said, it's going to be working in groups of about between 2 and 4, preferably 3 or 4, just to keep the number of engines reasonable. We're going to be walking through how to select which fuel and oxidizer we want to use, how to easily calculate the combustion results of what temperature is going to come out, how much, how many moles of products, all that crap. We're not going to do that manually because no, that's grad level evil combustion work. So we're going to use a NASA calculator that is very friendly and provided for free. how to design the supersonic nozzle, then toss all of this into SolidWorks. At some point, I know some of the people here aren't engineering majors, so you don't have access to SolidWorks, but we'll make sure that you get access to SolidWorks. And if you are an engineering major, probably should start downloading SolidWorks in general. We'll do some fluid simulations, again, in SolidWorks because it has a decent fluid simulation module. So you can see if the kind of computational fluid sim actually matches up with what our estimated thrust and other parameters should be. And at the end of that, we'll talk about how to actually get the propellants into the engine, which will be the fuel and oxidizer injectors. This is the super complicated parts of this, really. We're not going to go too in depth on the feed systems above it, but we will hopefully talk about that later in the semester, depending on how we look for what spring is going to look like more than anything else. At the end, again, depending on how much time we have, we'll talk about how to design the engines to be manufactured, whether that's like 3D printing, the way we're doing the Regen engine, machining out of stock, the way we did the Methylx engine, or something else. We'll talk through how to design for those things. And then, again, if we're actually here in the spring, we'll select one of the engines as a group, work through how to make it as good as we can, and actually build it. So the engines are going to be on the scale of the IPAGOX engine for the ones that we actually want to build. And we have a small test stand for that hopefully we will get to hot fire. Jackson, anything to add on that? No?
I think that's about it.
Are the Sims and ANSYS?
No.
No, I mean,
If you
Ethan,
want to, go for it, but
No, I don't want to.
our boy Ethan can do a kind of outside lecture on ANSYS, but I've never used ANSYS. And SolidWorks FlowSim is
in SolidWorks and easier to use.
Wait, you can do combustion in SolidWorks?
Oh no, we'll take the
Oh, no,
combustion.
no.
We're not doing combustion sims. That's
I don't even know if ANSYS can do. Well, ANSYS probably can do combustion, but
um,
That was
ANSYS can do
the
combustion.
NASA calculator that you were talking about.
Yep.
Oh, okay.
yeah.
My fault.
good. So we're fairly close to 9, but obviously we'll stick around for a while. For Thursday, we'll be meeting at 7. And if you guys have people you want to work with for this, come with a group, please. If not, at the end of the meeting, we'll split people up. General questions? Did we go flying through this? Because we probably did. We'll be going in a lot more into depth on how to actually do the things and make the decisions later.
Can I ask about SolidWorks?
Yeah.
So I'm not an engineering major, like I'm a physics major, and you guys said that you would like find a way of providing that to us, but also I have a Mac. Is it possible like y'all could also provide a virtual machine or no?
This is a good question.
There's a couple free virtual machines, but yeah, you're right. SolidWorks does only run on Windows.
Right. Like I have a Windows virtual machine, but it's kind of shitty, and I don't know if there's a better one that y'all have.
Mac has Boot Camp. I use Boot Camp.
Right, but I don't want to like have to do the dual booting. I'd rather just run it in a window. It's just annoying. It's personal preference.
If you're looking for the best one, I'd say probably VMware, but that's not free. If you're looking for free ones, VirtualBox is okay, and then
That's the
there's a
one
few
I
other
use.
ones out there.
Yeah,
all right.
I use VirtualBox and it's okay. But is
Wait,
that
I think Northeastern actually provides VMware.
they do?
They only provide it for COE.
Oh, okay, never mind.
COE one.
Yeah, so if I'm not in COE, like they wouldn't provide SolidWorks anyway.
You can
So-
request SolidWorks.
Right,
There's
if-
including licenses.
So what I'm asking is if I could request, like, do you know if I can request SolidWorks from them and also request a virtual machine?
I honestly have no idea.
I was actually looking at the COE website for someone else today, and the COE does have 500 licenses up for grabs for non-COE students every year.
But is that for SolidWorks or VMware? That's for SolidWorks,
For
right?
SolidWorks, yeah. I'm
Yeah.
not sure. Yeah, so I don't know if that's gonna help.
Do you know who I would go through to like find that out?
I would probably start by talking to Shayla, since she's kind of coordinating this intro for everyone, and they're having the same problem in other sections.
Okay, for sure. I'll send her an email.
All right.
Yeah, I'll put the contact. I know I need to talk to a couple people, but I'll put the way to request SolidWorks at least as a non-COE member in the Discord. Again, is anyone here not in the Discord? I just want to make sure everyone's.
Yeah, that and the Google Drive.
Yeah, I just shared everyone who responded to my Google form, the Club Google Drive. If you didn't respond to the form, please just email me, because you really need to be on the Google Drive. That's where we're going to house pretty much everything. The safety form. What did you? I'm not sure what you mean.
Are we supposed to have a safety form?
We're not going to be doing any in-person work, so I don't think so.
Yeah, I think you're good.
The only thing that's going to happen is at the end of the semester, whenever we finish designing the engines, we'll 3D print one of each and send them out. Hopefully, I think most of you are in Boston. If you're not, we'll ship one to you. You should have gotten a invite. I shared it with everyone's Husky emails.
What are you 3D printing the Regen engine out of again?
Inconel 625.
How do you spell that?
INCO.
I'll just put it in the chat.
It's like stainless steel, but like cooler with a lot more nickel.
Is that what SpaceX uses for the
Super drives, yes.
Yeah.
Any other questions, comments, concerns? The AeroNU website will have some content, but it also got nuked because we tried to transition who owned it, and it broke when we did that. So
Wait,
it's
when
being
did that happen? Do I see it in the new one?
the new one's a splash page because Cam Bracco built it in a day.
Oh, haha. I mean, this is
But
For
most
those of you who need access to SolidWorks, have a Windows machine and are not in the COE, I would recommend getting on that link that's in the Discord. I'll throw it into the prop chat and getting a hold of those licenses because there's only 500. So.
Yeah, we're going to probably stop using the email chain after this week, just because it's a pain for us, and we're going to do pretty much all of our communication through the Discord anyway. So I think I've tagged everyone with the intro prop role, so you should be getting notifications from that channel when we tag it. But If not, again, just let me know and I'll make sure I add that. Yeah, if not, if anyone don't have anything else, feel free to leave US on Thursday. Ideally, make some friends, come back with a group. If not, we'll assign you at the end of Thursday. If you have any questions, feel free to stay and hang around here.
Thank you.
Thank you.
Thank you.
Thank you.
Thank you.
Thank you.